Hello everybody, welcome to another stream. How we doing? So last stream, what were we doing? We were adding normal maps to the material as a second step after the fractal noise material generator. Now, at the end of last stream, was getting some artifacts, these sort of squiggly artifacts on things. I don't know if I got a picture from the past, maybe. I might have one laying about. Wrong button. Ain't that one. Ain't that one either. Alright, I don't have a picture. We was getting these odd squiggly artifacts. And they were coming from the fact that we were sampling an octahedral map texture, so one of these guys. And inside here was essentially getting a normal back encoded in octahedral space, right? And then would unpack that octahedral. Yeah, it was confusing, but so what ended up happening was we would sample. We'll sample into this texture for a position on the sphere, and we'll ask what is the normal for that. And again, that would be encoded in octahedral map layout. So we'd unpack it and then get our normal. Now the problem is that would have been interpolated in octahedral map space. So you're getting this weird interpolation between a 2 by 2 neighboring pixels. And it was causing these weird squiggly artifacts in some places. And unfortunately it wasn't really good. So what I ended up doing in the end, I did this off stream, so let's just quickly recap it, is I ended up just changing to using regular spherical mapping and tangent space normals. And it got rid of all those problems. Now the reason why I was doing octahedral mapping in the first place is because I was thinking I need to encode it as like a cube map in a sense. An octahedral map will allow me to use like one texture instead of like 6 for a single material. And then, so I was thinking I couldn't use spherical mapping because if I had a texture like this at the top and use standard spherical mapping where I wrap it around, at the top we'll get these sort of poles where the x coordinate goes so fast over this area here that it will just look really weird. But then like when I was thinking about it more, after bump into these octahedral map problems, is actually when I generate my materials based on a 3D position or a normal, or using the normal basically, which is like a Cartesian position on the sphere surface itself, I can basically achieve an image like this, where it's a corrected texture map, where it produces it doesn't look like it's funny at the poles. This one looks like it's funny at the poles here because they are correcting this texture and they didn't have a high enough quality here, and it was causing this to be very low resolution in a sense, and thus causing that sort of blurring. Now, because I've done it, because I'm generating the texture from the normal, I'm getting proper high quality. It's not from a texture which was not in the other perspective. So at our poles, it is completely fine, which is quite nice. So yeah, this is some little debugging thing I added as well, where the green is the translated normal in world space, the blue is the translated normal in local space, and the red is the original surface normal before the normal map comes in. So yeah, the blue and the green are the normal map translated normals. So yeah, get some nice looking effects there. So yeah, just to quickly show off the rest of them, and then we'll go into the other debug thing I've done. So that's another one with a normal map, which is quite good. Here's this one tests two different materials being merged together into one, and then saved that into a single material basically. And this is a sort of a not very rough metal object. It's got some artifacts, and I'm wondering if it was maybe a daytime environment map, would it look better? I still think we can do better normal map generation basically, because it's looking very stretched here. It looks like it's basically only pointing in this at the same pixels kind of ish. And yeah, I don't know, maybe a better environment map and perhaps better generated normal maps. I can still work on that code, but for now, I think it's pretty alright. It's better than it was, right? So I just want to show that I'm doing it with tangent space normal. So I want to show you what that is basically, the debug code for that. So if we go to shaders, and then we hop over to the calculate surface color, which is where we calculate the surface color, you know, based on all the shading properties, and we do material shading from here. Now I've got these debug things. Where are they at? Aha, these ones. So enable those, and we'll disable these. So what I do now is I sample from the normal map, and it's encoded as float 32 times 2, 1616 unorm, and I reconstruct the Z. So this is already a bit of compression. Basically, instead of 3 channels, we're going to need 2 channels. And I was hoping to get it down to 2 8-bit channels, but that's not possible. So we can't BC compress these, which we'll be looking into doing BC compression of the other textures later this stream. So what we get this in, this is the PAX normal and tangent space. I run it through this unpack normal map. So this is going to reconstruct the Z component from the, so it was a normalized vector. We took the XY and packed it into a texture, and now we're just reconstructing that here, like so. Then we have the original normal in local space, and we calculate the bitangent and tangent here. So I'm going to show you those visualizations now so it makes more sense. So effectively, imagine you've got this sort of flat texture. Yes, here's the tangent and bitangent basically. So the Z is sort of pointing towards us. That one is your normal, your original normal. The tangent and bitangent is the red and green. I guess you can call them whatever you want. I think I've called my bitangent the green one, so the Y, and my tangent is the red. But yeah, I don't know what the standard is on that. But so the basic idea is we have our sphere maps texture, and I can show it actually in the texture viewer. Oh, I thought I pressed a button there. Stop that. Cool. So here's the texture viewer. We have the normal map, like this. So it's encoded as 1616. So you're only going to see green and red, right? So where it goes to the right and where it goes up, basically. Well, so to the right and left and up and down, but it's encoded as a unorm. And we have to we bring that into signed norm, and then, yeah. Now, I don't know if you can, yeah, there's a signed norm. I don't know if that makes too much sense, to be honest. Yeah, that's not worked as I thought. Ignore that. But yeah, so there's the basic idea of that. And so essentially it's like, how much is it kind of a little bit to the right, how much right and left, and how much is it sort of up and down, basically. And the right and left will go across the red vector, and the up and down will go across the y vector, and the z will be reconstructed, right, kind of thing. And that's basically tangent space normal mapping. So I couldn't get tangent space normal mapping working in an octahedral map layout. I couldn't get that to work. So we're going back to using spherical map for everything. So here's the spherical map for, here's a spherical map, like standard sphere texture map. And you notice that this is where the poles would be at the top, and it's just getting straight. But we're able to generate high quality here because we're generating every single pixel by taking the normal of the sphere at that point, and then coloring it just based on the normal and encoding it at the pixel where it translates into. So yeah, there's no issues in quality at the poles as well. So it's pretty nice. Okay, so that's basically the rundown on the normal mapping. So I can get it better than 1616 unorm. If we compress it any more down, it's gonna be real bad. So what we're working on today, let's go to the material plan, is I want to generate so these are layouts of our textures basically. We're storing albedo in 888 sRGB. We're storing emissive in 888 sRGB, with the A being the emissive strength. And then we've got roughness and metalness. Those are packed into a single one. Oh, they're down here. Yeah, packed into a single one. Then we have height 16 unorm and normal 1616 unorm. Now, this is the uncompressed packed textures. What I would like to do is have compressed versions, because compressed versions allow us to use less GPU memory. They allow us to also use less memory bandwidth when we try and render. So texture memory is more likely to be in cache, right, or use up less cache and that sort of, and transferring from main memory, right? So if we use the built-in hardware block compressed texture formats, it will speed up the game basically when we're paying the cost for sampling textures, especially like 4K textures. So if anyone wants to know about block compressed textures on PC, you basically use BC compress or texture. Block compressed texture, the BC texture compression format. On Android and iOS, use ASTC, I think it is, or ATSC. No, ASTC texture. ASTC, that's it. So this is like the mobile one. And I don't really know too much about this one, but I know that it isn't exactly a one-for-one for BC. So on PC and consoles, you just have to worry about this type of texture format. So essentially, a better name would probably have been a tile compressed, because to me tiles are 2D, blocks are 3D, but these have been named like this way for a long time, so they're not going to change it. Now, so all it does is it takes typically like a 4x4 block or tile, and it will compress that down into something like 16 bytes or something like that. And in hardware, when you sample within this block, it will decompress it, or you reuse some previous decompressed thing. I don't know how it exactly works, but it's faster than doing it yourself, basically. So they're built into the texture format, or to the graphics APIs. So I guess I can link this blog for those interested in reading into some more details about that. So the cost is, obviously, this is a lossy compression. It's not a lossless compression, so you are going to get some, it's not going to be as good quality. So this is why I want to have a way with a flip of a switch, maybe in the build system, or a flip of the switch, or depending how crazy things go for the game, we might have build the uncompressed and compressed ones, so you can just flip them inside the game themselves. We'll see. But I think we'll have an uncompressed path and we'll have a compressed path, so we can like toggle them to see like, hey, are they actually like, are these visual things that I'm seeing caused by the block compression itself, right? So just for like debugging purposes. So essentially we have BC1. Now this stuff is not really, it might be a bit hard to follow. There's like BC 1, 2, 3, 4, 5, 6, 7. Like BC 1 all the way to 5 are kind of the same, but they've made for like different sort of format, different numbers of channels and stuff like that. So your BC1, which is for RGB data, between 0 and 255 or 0 and 1, right? Depending on how you want to represent it, right? So this is for like your standard colors, like the albedo map or the emissive map in our case. And then you've got BC4, which is basically, it's kind of similar to BC1, but it's only for a single channel. So this is for stuff like a material, like a metalness and roughness map kind of thing. And then you've got BC2, which basically is BC1 and BC4 together for RGBA data. There's BC3, it's so confusing, which is, wait, oh sorry, BC3 is the RGB data one. Right, what's BC2 again? I think BC, right, and then BC5 is two BC4s stuck together for R and G data, right, for two channels, basically. I forgot what BC2 is. Oh, BC2 is the BC1 with 4 bits for the alpha channel. Right. Okay. But yeah, we're just gonna, so we're not gonna be using BC2 basically. We'll use BC 1 through 1, 3, 4, and 5, because they're all basically the same. Hey Perry. Thank you, sir. Yeah, Nick Johnson is pretty damn cool. Yeah, things are going good, man. I got my normal maps sorted out. So we're doing block compression today. We're gonna be adding that to the renderer. Things are going very, very well. I'm yeah, looking forward to building this material builder and getting started on the editor. I'm working on some slightly secret stuff behind the scenes, which I would love to share, but it's a bit too early. I will share that later on, by the time we get to the editor side of things. So I found a block compressor. Oh, so here's the thing, right? Typically, there's tools to like block compress textures, and they do like really good job, like different quality levels and everything. Now, I want my build system to kind of be as quick as possible, you know, for iteration times, and also like, you know, it's just better if everything is as quick as possible, right? So what I'm going to try and do is take this open source block compressor, which doesn't really have quality levels and it's very simple code. I've seen another one by Microsoft. Believe it or not, it's Microsoft that's providing this, which is even more complicated, but it probably does a better job. Now, we're going to try and implement this one. It's only like 600 lines of code, but it implements BC 1, 2, 3. Wait, is it 1, 3, and 5? But obviously it does 4 because 5 is 2 4s stuck together. So it does all the BCs basically that we want. and it's in a single file. So we'll port this over and we'll see like how good of a job it does. And the reason why I want it in shader code is because we're building a material builder. Well, it builds materials in pure shader code, right? This is how these guys have been constructed, is purely with shader code. Yeah, that one needs to, we need either better environment map or normals. I'm not sure how we'll do that, but yeah, these ones look pretty cool. So what I would like to do is not have to take it from GPU memory, put it to CPU memory, put it to the disk, and then be like, hey, other very impressive block compressor program, take my file, read it into memory, read it into GPU memory, run your special shaders on it, and then put it back out to disk again. And then I'll read it in, and I'll put it back into GPU memory again, right? I don't want to be doing that. So what I would prefer to do is have a way to block compress it right away in GPU memory, and like all from my code. And then if I want to put out to a file on disk, I can also do that. So this means when I drag a slider, we can see it right away. And yeah, obviously I could view it in a uncompressed format in the editor, and then when we come out to the game, it's block compressed. But yeah, I want to see it all in the builder as well. Thank you, Pete. Yeah, they're looking awesome. Yeah, you can ask for advice. Hey there, JD Husk. How's it going? Yeah, you can ask for some Vulkan advice. No worries. Right, so with all that preamble out of the way, we're going to go into the Vulkan code base. And we're going to add support for BC1, BC, whatever, right? So we're just looking what they have here, and we'll be like, oh, I like that. So they've got BC Unorm sRGB. We'll probably do both of those. So the sRGB just means they do the auto sRGB conversion, which is kind of nice when you're sampling it. So we'll support those. We're not doing BC2, remember, but 3, 4, and 5. Oh, good. Right, I like the idea of that. So we're going to go into our gpu.h and find Alright, so by the looks of it, we need to stick these boys and girls together, or the sRGBs ones, because I've got this comment here saying, provide automatic conversions to linear when using them as a sample texture, but you need to manually be converted shader code when using it, manually read and write. Okay. So, BC1 sRGB. And there's BC3 sRGB, isn't there? From memory. Yep. Then we need to take these and we'll stick all these block compressors together down here. So these are unorms. And we have BC 4 and 5. Now they are supporting signed norm, right? Good old snorm. But let's not bother with snorm because I don't think we're going to need it. And it's just a manual conversion anyway. You know, times 2 take 1, right? But right, so let's put comments here so it's more understandable. So this is for RGB data. This is for RGBA. This is for R data. And this is for RG. Not confusing at all. Now, we should also document maybe how big they are such that you can alias them as raw bytes and write the block compressed data manually, because that's what we're going to have to do. So we want to say, oh, right, it's not really going to say it here. I thought they were going to say it. Okay. Vulkan BC. They got BC1 RGBA? Oh, plus optional 1-bit alpha. Yeah, we won't support that maybe. We're not going to support that. Right. Each 64-bit block. A 4x4. Right. So they use, so per block, so 64, okay, so a block is 8 bytes. So 4x4 block, 8 bytes. Eight bytes per block. So we'll just put these little comments here to help us remember what they are, because it's so damn confusing. Oh, and it's best viewers. Oh yeah. That's fooling basically nobody. I don't know how they manage to fool people with these. It's just junk mail at the end of the day. Who is that much of an idiot to do this? Raid? No, I'm joking. Right, man. It's just so damn dumb. Yeah, I saw the artifacts. Yeah, so I covered that like right at the beginning of the stream, Pete. So if you're interested in like the full detail, I guess watch back the beginning. But basically it's because I can give you a quick TLDR or TLDW, which is basically we were encoding them in octahedral map space, the normals, right? So when you picked up a pixel from this octahedral map, it was interpolating in octahedral map space, and that's where some of the squigglies were coming from, because it was interpolating the pixel value, and that pixel value was, so you got is basically another location on this octahedral map, right? And then we decoded that as the new normal. So imagine if the normal was pointing like over that right side, it would, when you sample this pixel, that would be the UV coordinate for that pixel over there, right? And then, but maybe you might have had a neighbor, right, which was pointing more of this red side. So what it was doing is it was interpolating between this pixel here and this pixel here kind of thing, and you'll get these sort of like weird squigglies, basically, like squiggly lines sometimes because of things like that. And then yeah, so it was just better if we wasn't using this sort of funny warped format. So we just went back to using spherical mapping, and I realized that, hang on a minute, I won't be getting these pole warping artifacts because I'm generating this kind of corrected texture map. Because because I'm generating it based on the 3D normal coordinate, my textures based on the 3D normal coordinate and shader code, and then packing it back down into this 2D thing. So my textures will look warped, but they'll have high resolution in the warped areas, so I won't have this problem. So I end up just going back to sphere mapping, spherical mapping. So, and that's how I fix the artifacts mostly. We've still got some though on this fully metallic one. I think my normal map generation could be done better, and the environment maps could probably be higher quality. But that's for future me to look into. Not a problem for now. Yeah, it just requires like knowing like how the thing works, like what you're doing. Yeah, I. It's one of those things where you sort of like can't think about it on the spot, but when you sort of take a step away and you're sort of just letting ideas come to you, like, those are the problems, you know. I was wondering if I should learn Vulkan OpenGL for my first graphics programming. Right, JD Husk, are you still here, my friend? Sorry I've taken some time to answer your question. The answer is neither. What I recommend is that you write a triangle rasterizer from scratch. So what I recommend is that you try maybe something like this, where you learn how to rasterize your own triangles in software purely on the CPU. Now I don't know if this is the best tutorial, but there are plenty out there. Now why do I suggest this? Because OpenGL and Vulkan are abstractions over GPUs. GPUs are designed to make rendering go really fast. When stuff is optimized to make stuff go really fast, it's also very complicated. And they're abstracting over many different GPUs, which makes it even more complicated. So you've got many layers of complication for someone who's just trying to learn and pick up graphics programming. So what I recommend you do is you learn what they are doing for you, and you will have a much better understanding than someone who just went and learned OpenGL or Vulkan like me. You would, rather than doing it the hard way, you would have done it the easy way. So this is the way that people would have done it back before everyone was spoiled with hardware accelerated GPUs. So what you can do is you can study, whenever you see, you learn how to rasterize your own triangle, and then you can sort of look into OpenGL and Vulkan and be like, oh, they have these things called vertex shaders, or they have these things called pixel shaders. Then implement vertex shaders and pixel shaders inside your software renderer, right? And basically try and build your own kind of easy to use OpenGL or Vulkan purely in software. It's going to be far more simple, right? And you'll be able to basically render whatever you want. It's going to be slow, but it's going to teach you a whole lot. Now, to get something on the screen is going to be difficult. So you got two options. You can basically use STB image to write out STB image write. So write out an image to a file and view your result rendered to a PNG file. The other option is you can use SDL2 or 3. SDL3 is probably a good bet these days. Use SDL3, and with SDL3 you can open up a window really easily. And they also have a way for you to take a software rendered set of pixels, so pixels from the CPU, give it to SDL, and it'll put it on a window for you. So you'll be able to basically render frames like a video game would and put those to the screen. So that'll teach you a whole lot more than just trying to learn OpenGL or Vulkan. So I highly recommend you start there for your first graphics API. If you got any questions, feel free to ask away. Anymore, feel free to ask away. I also fall into the verb learning first graphs API and now going backwards to resources and digging up the CPU. Yeah, exactly. Yeah. There's always sort of like fixed function stuff going on, and it's so damn confusing reading it. But if you sort of implement it hands-on, you really do get a better understanding of it. BC3. I'm sorry for this blinding white screen. I apologize. Right, it's 128-bit. Okay, so it's not really a BC4 then, is it? And a BC1. Right. Then maybe it is. No, it might be a BC4 and a BC1. Right, so this is a 4x4 block with 16 bytes per block. So this can be done in a U32 times 2. This was done in U32 times 4. So the R would be a 4x4 block with 8 bytes per block. And then, I don't know, it sounds complicated. All I want is to create Doom 93 using C++. Okay, so if you think that sounds complicated, try and look into Vulkan and tell me if you think that's complicated. Just try it. So let me also tell you. Oh, let me ask you a question. How do you think Doom 93 rendered its graphics? So I would love it to give you this. There's someone, you know what, let me see if Not So Red is around. I need to like bookmark this page. Let me see if I can summon Not So Red. Like I gave Not So Red this advice and he went like just to the moon and back with this. And you have to see how simple this actually is and how easy it is and what you can do in like 1,000 lines of code. Like, it's just insane. So, let me. I know I have. Right, I'll summon Not So Red. Hang on a minute. Vulkan or custom API? No. Wait, you answering my question of Doom rendered in Vulkan? No, obviously not. It wasn't around back then in '93. Custom API. What do you mean by custom API? If you remember correctly, old Doom is not even 3D. It's raycasting. On CPU can achieve this kind of graphics. Yeah, exactly. They couldn't achieve proper 3D. So what they did is they did it all. And they didn't even have hardware acceleration back then. They did it all in software. They weren't even rasterized in proper triangles. Right, I think not so red is. Alright, Wajilla. Hey there, Wajilla. How's it going, sir? How are you? Right, what's the other one? I'll close the damn page. Right. BC5. 128-bit, because it's two BC4s, of course. Boom. Right. Now I've just got to plumb these in. Alright, so before we go and link these up to the Vulkan ones, these are in blocks of 4x4. Right, so the way Vulkan does it, right, is that your textures have to be rounded up to the nearest block. So, we are going to... So I think, is there a certain sort of blockiness that's... Is there non-square blocks? Yeah, there is. ASTC is non-square blocks. So, we need to define a 2D, because there's only 2D blocks. Could have been called a tile, but they're called blocks. Block dims. So we're going to imagine everything has got blocks, right? But the standard pixels, pixel textures would just have a 1x1 block, right? Now, shoot. No. Rewrite my renderer. Oh days, I've done that too many times. Yep. How's... What? So why did you rewrite your renderer? What was the... Did it not quite feel right? Like the shape of it and everything. Hang on a minute. Hang on a minute. What about OpenGL? It's terrible, it's old. I'm telling you, you're learning an old API which is going to be more complicated than writing a software renderer. Guaranteed. 100%. OpenGL is not going to teach you anything. Vulkan's not going to teach you anything. It's going to teach you that you're going to have a headache, and it's going to test how well your perseverance skills are. And it's not the thing to learn for your first graphics renderer. If you want to learn, you learn from the first principles of what it takes to rasterize a triangle. And that is the best route. No one's going to tell you that. Why did I type 1616 Unil? BC1 sRGB, BC3 sRGB. I need the other BC ones down here. Got messy as I learned about Vulkan, figured out huge structure changes would be needed, and rewriting from scratch in more structured way would be better. Right. Okay. What do you mean by huge structure changes would be needed? What do you mean? Oh, okay, then you're reasonable more structured way. Right, did you have more... Yeah, I'm not sure what you mean by a more structured way, though. But yeah. And these are... Did I not link to the tutorial? I linked one here, didn't I? I'm not sure how good this one is. Let's just setting up it in a browser, though. Let me see if I can find another one. I'm trying to give you the link to Not So Red's repo, because Not So Red's done exactly Yeah, software rasterizer, you don't. Triangle rasterizer is what you need to search for. No. Yeah, try it. This one is alright. We're crying out. Get out of there. This one. Yeah, this will teach you some things. But yeah, look around for triangle rasterization. Like a bunch of different websites. And then try to look at how OpenGL works and try and re-implement it. Or learn how the triangle rasterizer works, like the pipeline stages and everything like that. And like these things basically, the input assembler, the vertex shader, skip tessellation geometry, but rasterization, turning those into pixels, and a fragment shader. So look at, after you get your triangle working, look at vertex shader and fragment shader and color blending, and try and fit these things into your rasterizer, and that will and then from then on out you can basically render whatever you want. You can render 2D, 3D, triangles and everything. Ah, Ransel found it. What a lad. Right. Hold on to your socks. And also, feel free to join the Discord if you want to come and hang out and chat about stuff off stream. So, basically, right, I gave this advice to Not So Red, and then he went to like the moon and back. So this is all rendered in his software renderer, full like PBR. I don't know if it's got even subsurface on here, is rendering like a human skin. It looks quite alright. And he's rendered that 3D model, this texture quad, and this 3D model as well. And he's done it all on CPU, and he's re-implemented like vertex shaders, pixel shaders, and it's not even a lot of code. So I recommend you looking at this repo and learning from this as well, and implement your own, just inspired by this project, I would say. So where's the bookmark button? There we go. Now I can finally. So in the source here, if you see, literally it's a single header, right? 1,000 lines, right? If you did 1,000 lines in Vulkan, you wouldn't learn any of this, of what it takes to render something, and you would probably just about get a triangle on screen. With this, you'll be able to get many triangles up on screen. But yeah, he's written his own software render. Take a look at the API. And it rasterizes triangles, pixel shaders, vertex shaders, and he's kind of looked at Vulkan and tried to sort of learn how the API kind of works under the hood in a way, and made a very simple version of Vulkan. So, yeah. Highly recommend. Biscuit is intro program on YouTube. He also has a Polygon rasterizer 2-part video. Yeah, if you can link that, that'd be good. BC1 Unorm. Yeah, I think these are all just going to be Unorms. BC3, 4, and 5. Good. Alright, let's get these quickly up here. So for conclusion, I should write my own rasterizationer, not a renderer. Yeah, start off writing a triangle rasterizer, and then write a renderer that utilizes that software rasterizer, right? And look at Not So Red's one for an example, and you've seen the stuff that you can do with it. I'm trying to achieve something like that. By then, you would understand so much more than you ever would after doing 4 years of OpenGL. And you can do it in months. 100%. You understand it as you understand it from first principles, which means the building blocks of how things actually work under the hood. And then from then on out, once you've done that, come back, come back to the stream or on the Discord, ask what you need to do to learn Vulkan, and I'll give you the next thing to look at. And then from then on out, you can learn Vulkan. But I would probably recommend that you, to do your project, you could probably just do it all in that software. Wait, could you? You wanted to make a Doom game, isn't it? Yeah, after that, I would say there is a if you want to. So after you've done that, or maybe it entirely depends what you want to do. But there's a thing called like a raycaster. This is what Doom. This is how like Doom basically works, is this sort of raycasting, they call it. If you want to build a one-to-one how Doom works, this is the technology they use, right? It's called raycasting. It's kind of pseudo 3D. Just, yeah, this is a good resource on it. This is really good. But if you want to actually do proper 3D, do the software rasterizer first. Definitely. Whereas that Doom way is like a pseudo 3D fake, right? All right, so we're just putting some strings in here. We're just integrating these new formats into the renderer, and then we'll do the conversion in the Vulkan code to the Vulkan format. We need to also add the new block compressed. So number of channels. So 3 channels, 4 channels, 1 channel, 2 channels. Not confusing at all. Right, bytes per pixel. Bytes per pixel is no longer a good metric since we're adding block compressed things. So we should be saying bytes per block. Since a block textures are only addressable per block. All right, so this was 8 bytes per block, 16 bytes per block, I think. Hey, you're back already. Huh? Oh, okay. I thought of that, right? Hey. Right, 8, 16. Four, 5. Right, let's go into that header. Right, so 816, 816. Voila. Right, so the final thing to get done is to take all of this and go down to this new one. Right, hang on a minute. So we'll add these sRGB ones in here. True, true, and link to their unorm variant. Nice, nice, nice. So this block dims, so we need to return two-dimensional things. So here's the thing, right? That everything is just going to be one by one except for the new block compress ones. Okay, so these will be 4x4. And there we go. So with all this information, we can now have proper recursions, and it's integrated into the sort of the GPU layer which sits above Vulkan. So when we create the texture, so let's go texture initialize. We've got to be careful. We've done a bytes per pixel. We're gonna look around for all those places and change them out for bytes per block, right? So rather than BPP, it's BPB. Now, we've just got to be careful as well on those, which we'll get back to in just a minute. What I want to make sure we check is that when we initialize our textures, that everything is correct. Right, here we go. So we need another assertion. And that assertion is that the mod I don't know how I want to say it. So it's like we want to make sure that the 2D, right, so you want to know if the thing is block compressed. Do I want that as a, yeah, so when you get the bytes per block. No, not bytes per block, sorry, I'm talking about the block dims. So that'd be GPU texture block dims. I've got a resource format for crying out loud. GPU format. Much better. Right, so we index that with the format. Voila. Now what we're saying is if it is, so Boolean is block compressed is any greater than and 1. So if any of the xy's are greater than 1, then it's a block compressed format. So what we're saying here is it's not gonna, if it's not block compressed, or that the mod of dims.xy so I think you can block compress. So I think these block compressed ones have to be 2D. Does it say that? They have to be at least 2D, I think. Oh, I've not got 1D textures. That solves it. Less features, the better. So we're saying that you mod that with block dims, and that if that has to equal 0, right? So you say all equal zero. Beautiful. And all we're saying here basically is, you know, dims block compressed dims are not aligned to block dims so dims.x, dims.y, and then block dims.x, block dims.y. Right, there we go. So that's all I wanted to do. Now our next thing is we need to check those bytes per block and just see, like, is there anything to do with, now we're talking about multiples of block rather than multiples of pixel. Is there anything that we need to do? Is any of the code broken, basically? So let's check the logic. This is the upload texture. So we take in like an offset and a dims. Now, this here, the offset and the dims, again, have to be aligned to a block. So that's another assertion that we need. So I guess we just copy this. So let's go to here. Bytes per pixel, yep. So that'll be a resource texture format. I already said that this is a texture overlay. Alright, that would be pretty ideal. Well, the upload buffer, that would also be pretty great if it is a buffer. Well, buffer is quite easy actually, don't mind me. Alright. Good. Now, what we're trying to say is that this thing, it's got to not be block compressed or that they're all equal. Now, that is for dims. So you've got the same thing for offset as well. Pretty good. Great, so there's another place where this happens. So this is for upload, there's also read back. So we definitely got that one to deal with. Bytes per block, read back texture, plop that in there. Job's good, same thing. And we're gonna have to, take these assertions here and put them in here too, because that's something that I've definitely missed basically. And there's the buffer up here. I forgot to put that in here. Oh, I've already done it here. Parse Henry solved that problem, but not the others. Okay, so there's one more place in this GPU code, and then we get into the Vulkan code, and then we can go and write that custom shader. So bytes per block passes the auto copy. Offset and dim, same thing again. Let's plop that in there. Maybe there could be some abstraction here, but copy and pasting code is just alright sometimes. Later we can clean up the code and ruin it. It's typically what happens. Over abstract it later on. I've done that many times. Right, okay, I've already got it in, oh no, where is it? Read back. Auto copy. Screw it, let's leave it. Right, so I think that's it. Full circle. So let me just double check the GPU header. Just check the whole API. It's not big, it's very small. If there's anything to do with the dims, let's write dims. So there's, when you create the texture, that all goes through the same thing, I think. Maybe not, let's just double check. Right, these need it as well. But the reinit static. All right, they're gonna need it. So I could make a function to put all the assertions in, but oh well. Oh, these are them. So it was the texture reinit. They need it there like so. And then the other one was the texture alloc. Right, what else? Let's go back to the header file. So where else we've got some things called dims. Right, texture init we're done. Yep. This sort of like max dims thing, not really, doesn't matter. Copy. Did we end up using this in the end? Oh, that's the entry, don't mind me. I guess that's when we get the result back. Read back, upload, we did that. Right, texture copy, we got to copy in blocks. Yeah, texture copy is another one. Yeah, I think that's the last one. Yeah, it's the last one. All right. So where we've got the offset ones, we'll take this code here like that. So texture copy. So texture copy also needs these assertions. Probably stick them here. So we'll get the I assume they have to be the same formats, right? Did I even check that? No, they don't have to be the same formats. Yes, I think you need to check this twice. Oh, what's going on here? It's called DST in it. Right, so copy DST offset. And then copy DST dims. I think that's the thing. Oh, it's copy dims. Nice. Then we'll do the same thing, but for source. So DST and then source. Right, so now put in those extra assertions. So you could just use the Vulkan validation layers, but yeah, those are quite beefy. And we do use them though. But this will also catch it across different APIs whenever we do that as well. So, and it, yeah, that's it basically. And it's probably a lot more readable than the Vulkan ones, because the Vulkan ones spew out a lot of stuff. A lot of words all in one line. Not the easiest thing to read. Okay, so now it's all done in the GPU layer. Let's get down to the Vulkan layer. It's very easy. I just got a lookup table that translates the formats over, and it should just work. So basically, we've got the BC1 sRGB. So BC1 sRGB block, BC3 sRGB block, and then we take these two, pop down to here at the bottom where I've put the other ones. I'm keeping the same sort of order. sRGBs are in their own little special section. So we've got the unorm, like that. Then we've got BC4 and 5. Now, I've got BC3 wrong. BC3 is sRGB, sorry, is RGBA. It's too many words, too many letters. Oh, they don't have the RGBA stuff in the name because there's only one variant. Okay. So it's BC4, BC5, and voila. So that's all we have to do for the Vulkan layer. It's just fill in the lookup table, and the rest of the code just works. Right. So now we've got the block compressed stuff in. Now we're going to go to the materials, and we're going to fill in we're going to make it we're going to have ways of initializing this thing called a material texture. So this is just the material textures filled in with a full MIP chain going down to 1x1 pixel. Maybe we'll have to go to a 4x4 pixel, but yeah, one block basically. Yeah, maybe we might need to do that. But yeah. So we've got a way to initialize one of these. And initialize full MIP chain. But what we want to do now is make this kind of optional. It's like, what is, or not optional. We want a way to say like, hey, what is, we want to know if this is compressed or not. So we might have this just as a global, to be honest, because I don't really want to sort of unblock compress a particular material. Like this structure is only for when you have a single material that you're sort of making and then you're saving it out to disk. We've got another structure where it's actually like a full-on cache with arrays of these things, like array layers. Right, so it should probably be a global somewhere. Now, I might put it in my settings. So we go to my settings.enc. I think we'll have a global for material block compression. Yeah, I think we'll roll with something like that. Material compression as a setting, and we can just toggle it by hopping open the settings and just see the differences, right? I think this will be pretty wise thing to do. I shouldn't put this smack bang in the middle of the bloom. Let's put it down here, something like that. This be the material compression. So this is all will be auto-populated in the settings panel we've got. On. It's on by default, I would say. So if we, yeah, we'll see that in this. We're just going to regen it though. So it's scripts code gen. Shoot. So that is in graphics shared in code. I added a new thing and then didn't bother doing it in the end. Alright, so regen. So we'll be able to grab this from, so we want to be able to say GPU format. So I have albedo format. And we'll simply just do a global settings, graphics, material compression. If we have compression on, we'll be using format BC1. And then we might be able to use sRGB, but the problem is we've got to alias it. Yeah, I think we can do it. sRGB. I think we'll have to make texture views though, so we can view it uncompressed. So that'll be GPU format 888 sRGB. So there'll be a wasted 8 bits in this one, because I haven't figured out what to do with that. Happened with the music. Okay, so next one is the not albedo, I meant to say emissive. So it's going to be 888 sRGB again, but the final 8 channel is going to be the emissive strength, and we sort of just multiply that by something. So that'd be 0 to 1, we multiply it by like 32 or 64, something like that. And then that will scale the rest of the 8 bits. The 8 bits. So that's like an emissive strength. So for that we use BC3. Next is the metalness roughness, which is going to be a BC5, which is 2 BC4s. So the norm, that's 88 norm. And the other one is the, oh, that's it. Yeah. That's all we need. Amazing. Cool. So that means then here we can replace that with the albedo format. Then the emissive format. We are going to try and get rid of emissive strength as a separate texture. Something I've still got to do. So that'll be a metalness roughness format. So let's go around and see if we can obliterate emissive strength as a separate texture. Then we don't have to go into 2 different memory locations, right? The data when it's needed together is next to each other in memory, hopefully, type of thing. You know, it's sampled rather than 2 extra samples, we just do 1. So let's look for emissive strength and see where else that is lingering about. So it's in the sort of like gen material as well as a separate thing. Don't do that. We'll yeah, 16 float, we'll get rid of that as well. So that's in the shaders. Color grad. Shoot, hang on a minute. So no, I think we want metalness roughness separately. And then we save them out. So in the material generator, if you have all the channels, if you have all the properties in their own textures, this means that what's the point of packing it down? You won't get that good. No, we'll pack it all down into the same texture because I can write a custom visualizer. It'll be fine. It'll be fine. It'll speed up all the other things like downsampling and stuff. If they're packed as well, that's a good idea. So, right, I've got to finish all the stuff in the shaders now. So, color grad. Right, it's the problem is in this color gradient thing. The emissive strength. It will lerp in color space. lerp color space, which means Is that preserving the alpha? Or are you just dropping the alpha from that? Yeah, so that's not... Right, I think in this lerp... Okay. So I think in our noise generator, we'll have the emissive strength separate because it just makes sense. Because meltness roughness is separate as well. Yeah, that's where it makes sense. So we'll still keep the emissive strength as a separate thing as part of this noise material generator thing that we've used to generate our custom materials. That makes a lot of sense. So we'll leave that alone. It's just when we write it out to main memory, it'll be packed. So in the shader code, just get through all this. It's alright, it's alright, alright. Yeah. This is where emissive dot A is equal to emissive strength divided by some constant. So that constant might just go into graphics internal shared right now, and we'll probably have like an emissive... Have I written it in here already? No, I haven't. So we'll probably have something like graphics emissive max or something like that, like a max emissive, and I might just say 64. But you got 8 bits, right? So yeah, let's just say 64. So you can always change it, I guess, whilst we're developing it, at least. So then you... Yeah. So this will get it down to 0 to 1 value, basically. I could clamp it between 0 and 1, but... it's going to do that anyway, I think. Cool, so we don't have a separate channel for emissive strength anymore. There we go. Amazing. Right, so fill invalid. Have to worry about that one there. We get rid of that too. This is sampling the actual texture. So we'll be sampling a vector 4. This will be emissive, and then emissive will be set to emissive.rgb multiplied by emissive.a, which is the emissive strength. So I could probably label that better and then call it emissive strength. And then, yeah. So this is the code which actually does the material shading by sampling from those textures, which are going to be block compressed in a bit. Okay, so we've gone full circle. Let's hop into the internal shared. So this is the internal graphics header, which is shared between CPU and GPU. Let's see if it's got any emissive strength going on here. So there's this thing called a material index. We will delete that line there because now I've combined those into just emissive now. And there's another one here. So essentially we've got a material cache where we've got one texture which has a bunch of array layers, and each array layer has obviously its own sort of MIP levels in it. And essentially whenever you register a material, you get back a layer index and an LOD index. And with that, we'll be able to find the exact texture to sample from. So you have one. Yes, it's a little bit confusing. But the idea is you don't want to have the highest level of detail material loaded all the time. There's only like 4K textures, for instance. And then the rest, there's 4 times more 2K, then 4 times more 1K textures, and so on. And the lowest loaded one is about 64 by 64, I think, and there's 1,000 of those. So you've got an LOD. Each LOD has an array layer. It has one texture which has all the array layers in it and all the MIP chains, going down to 1 by 1 pixel for that level of detail. So just with a LOD, we can get back the single texture to sample from, and within that LOD texture 2D array is an array of layers. So you have a layer for a particular material, and that same layer you'll be able to access all the different PBR channels across the different material caches. So it sounds a bit complicated, but it means that we fix allocate it all in one go and just shuffle them around to the different areas, basically. Shuffle them around to the different LODs based on how close they are to the camera. So it's just pre-allocated arrays, basically, is all it is. So we got rid of the emissive now. This is up to a 32 times 4, a value between 0 and 1, obviously. And very good. So fill invalid. We don't have emissive strength anymore. Goodbye to you, sir. And there we go. Yeah, what happened to the test material? Yeah, we got rid of that one as well. Excellent. Right, so let's go back to the graphics side of things. So this is the CPU side that kicks everything off. Now, let's carry on looking around for emissive strength. This is that LOD cache thing. Right, when we initialize the material cache, we go over all the LODs. There's 12 of them, because that's how you get to 4K. So from 1 by 1 pixel, if you times that by 2, you've got 12 of them. You know, 2 to the power of 12 is 4K. So each LOD has one texture 2D array for however many slots it has, and that's the number of array layers. So it starts off at 1024, then it halves or divides by. It goes down in powers of 4. Right, it's too much anti-crest. Let's put something else on. Back to Nick Johnson, where we started. Cool. Yeah, so these have to respect the new format as well, like the compression thing. So again, that'll be a global. Now, thinking about it, we can't really toggle it in the settings. If we did, we'd have to reinitialize everything. So this is something, I guess, to work on. Yeah. We can get it working. It's not too bad. So again, let's get those. This is albedo format. Let's just grab those like that, and we'll simply just throw it in here like so. Here. All right, very good. So albedo, emissive format, and the metalness roughness format. So those either be block compressed or not block compressed. Nice. So let's keep looking around for emissive strength to see where else we need to delete. Did we delete that? Right, so there's no longer a texture to do a copy with when we load a material in. Right, so I think we've sorted that out. Now we've removed the emissive strength and combined it into a single one. So we'll load up the materials now. Yeah. So we try and run it. What we're going to get is... Okay, let's get it compiling first. When did I say it's a U64? I could have swore I put a .f on the end. Get out, there's a .f there. What have you done? I did clamp F64, of course. And yes, F32. Right, so there's a mystery 6 sitting outside the array for some reason. What are those all doing there? Right, they didn't highlight the 16, that's why. Get rid of it. Right, so it should run and then crash in the shader code or look invalid, basically. Right, we've got validation errors. Let's fix these and then we'll go to the next step. So this is a validation error because of why? Oh no, it's got creation limits. I don't like the sound of these. Oh, they actually put them on new lines now. Interesting. Right, so we've got a format of this. Texture 2D. Tiling optimal. It's returned format not supported. No, you bugger. So that probably is because it's got create. It can't because of create alias. Alright, so we've got either the max MIP levels. It's probably the max MIP levels. Because we've gone all the way down to 1 pixel. I imagine that's it. So we need to go all the way down to 1 block. Oh, it said it here, max MIP levels. Yeah. So we've got a little helper function. MIPS max from dims. Now, we kind of want to put in, like, let's figure out where we use this. We should kind of ask for a format as well, not gonna lie. Because then we get the block size. And then hey Perry Perry, could you recommend me some resources for custom reallocators? Never done one. Yeah. So for that, I would suggest Ginger Bill's custom allocator resources. You don't really need to read all of them. You just need to at least read the first one and the second one. That one's alright. Okay, read 4 of them. 3 lists and just read them all. But it really, the thinking starts changing after the first 2. I use pool allocators, but I have them typed, so I have a kind of an object pool thing in mind. Stack allocators are not used yet. I've just got some linear allocators for now. I'm just using those. That's all I'm doing at the moment for mine. I need to it's not the best at the moment, but it's far better than them using malloc. And it's a lot simple, more simple. But this will really just change the way you think about custom memory allocators and memory itself. And yeah, you'll be in the top 90% of programmers after that. I remember I saw the post on. There's that guy who runs the boot.dev thing, and he had this course that he did with TJ on learning about custom memory or learning about memory allocation in C. And they basically implemented a garbage collector. And it's like in C and learn about how garbage collection works. But so the one thing I like about that is that they actually implemented the thing they are using to understand it. That's great. That's a great mentality. Like that, if you do that, you'll go really far in your programming career. But the problem is that they are still using garbage collection and not really understanding that memory allocation is actually really simple. And if you just read that blog, you will understand and wouldn't have to use garbage collector. And yeah. The only thing about memory allocation, I think I know memory allocation, write my own malloc as an exercise. Malloc's a very general purpose. And sometimes you need that. I'm going to need a custom version of malloc, or a heap allocator, or a free list allocator, as they're sometimes called. Yeah, I'm going to need one of those. But they are very much a very rare case. You can do a lot with a linear allocator or pool allocators. They use a whole lot as well. Right, I'm gonna get a quick drink and then we'll start this block MIP. Calculate the maximum number of MIPs. Right. BRB. Right, welcome back everybody. So we need to make sure that we don't pass in too many MIPs to be generated for a block compressed texture, because as soon as you go past 4 pixels, it is too small because you have to go down to a single block. So we have to be really careful. So there is a sort of like GPU MIPS from the final dim. Interesting. So I think this needs to go the other way around. This needs to be to that one. Then this one needs to get the format. Yes, you get a GPU format, I think. And then I think you'll get like a block dims, GPU format block dims. And then you can call that function below, MIP from dims. And then that you'll pass in the, I think we'll pass in the format as well. We'll pass in the dims, and the final dim, so the final dimension we get down to is the biggest element, so max element of your block dims. Yeah. Now, I would like to also pass in the format in here for extra bit of safety, and I would like to make sure that basically final dim is equal to the maximum between itself and the result of that, basically. That'll do it. So we need to add this to the header file. And then everything that uses these functions. Albedo format. The thing is, it won't go down to 1 by 1 on the others. That'll be alright. Yeah, albedo format. Right. Right, so what format is this one? So that is the occlusion. Oh, right. Okay, so it's just GPU format. Float 32, 32 float, something like that. I think so. Yeah, I think so. Alright, so the other one was the... Right, Bloom. So Bloom would have been... Yeah, you know, I don't know if I like changing the API in this way though, to be honest. I think maybe... No, we'll do that. We'll do it. Alright, so this other one was in one place. So Bloom... That's just going to be a full... I think that's GPU format 16 float. It doesn't have to be exactly right because they're not block compressed. Cool. Amazing. So we tried that out. That should fix this Vulkan error where it was saying that it's a not compatible set of options, but I think it hasn't fixed that, unfortunately. So I'm going to look at some of these other things. It's saying it is the max MIP levels though. All right, let's go to my GPU info.org. See what I can find. So I think if we go to, what am I on a 7600 these days? Let's just select one of these. So did they bother doing it? No, but that'd only be for the surface, wouldn't it? Yeah, they've not got. Right. So what we're going to do is we're going to build a little bit of a debug thing in here. Error not supported. And we'll handle this explicitly and write a nice message out rather than this silly stuff, right? So, because I think it's not telling us the exact numbers, which they could do that, but they haven't done it for some reason. So when we do our sort of create texture, oh my days, in Vulkan. Create image, they call it. Not these ones. It is this one, isn't it? Yeah, texture in it. So texture initialize. Oh crap, go back. Yeah, 7.7. The 7.7 one fails. Interesting. Oh, 7.7 failed, but 7.1 did not. Interesting. Right, UNorm failed, but sRGB did not. Huh. Okay. Right, so what we're going to do is... Oh, we've put on storage and sampled, isn't it? Right, you can't have a storage. You can only sample. Right, you can only sample from... Alright, this is perfect. Maybe. Yeah. Right. So if we've got it as a storage texture, we're not going to use UNorm. But do we need a UNorm variant? So effectively in our... The way we handle sRGB is that we cannot use sRGB in a... What's the way of saying it? You cannot use sRGB textures as storage textures. So what I do is that if we have an sRGB texture format, I create an alias, right? I create two images, but they alias the same memory. right? And it works, and it's fine with the spec. So it's the same memory, but we have to tell it that it's aliased as part of a flag. And it seems to work fine with the sync code as well, which is great. Now so what this means that we can do is we can use it as a storage texture and read and write from it as a sort of a raw data. And then we can also sample from it as an sRGB texture, and it has the automatic sRGB conversion, which is actually very helpful sometimes. So there's sample textures and storage textures are separate things. So the thing that I have is I have a lookup table which translates it from this sRGB into its sort of unorm variant. And so when you write it in the raw bytes, you have to do the manual conversion into sRGB. Now, when you're viewing when you're viewing so I might not want to say sRGB. I might want to say maybe we combine this concept, whatever we've built. So these have to be mapped to 64 bits, right? So that'll be a 32 uint, right? And and now alias to 64 bits. This is 64. Sorry, 128 bits, I meant. So it's 32 uint. Because that's what these shaders are going to be doing, basically, is pack into uint4s or E32 times 4s, right? So we can probably combine this concept as, because the unorms have got to do this thing as well, is like, we want to say, is this a... I wonder if the sRGB matters outside of... It doesn't, does it? Right, so I think I'll change this concept into something like is... So yeah, we'll make it seem like a... So we could say is sRGB or is block compressed. And then we want to have that sort of like... Yeah, we'll see. Right, so 1 unorm, 4 and 5, shoot. 4, 5. 4 is 64, and that's another 128 bit 1. Cool. 108 bytes. Is it bits or bytes? Bits, that's it. Right, so we might, rather than call this like, we should call this the storage. So we could probably say, we can change this to being something like is or has different storage format. Yeah. And then so that'll be the new combined way of doing it. I guess we'll have to change the, it's true. So we have to change all those places. It has different storage format. And this would be the storage. GPU format storage variant. And that will just translate it into the what it's going to be represented as in when it's used as a storage texture. Amazing. Cool, so we'll go to the header file and quickly change that documentation on it. So I think actually I'll probably put my BCs up there as well. So we'll say sRGB textures provide automatic conversion to linear when using them as sample texture, but will need to be manually converted. Block compressed textures are also what we want to say is basically sRGB textures, sRGB and block compressed textures they can be used as sample textures, but they cannot be used as storage textures, right? Yes, it can be used as HCC sample texture, but not as HCC RO, read only, read write texture, any of those ones. To combat this, the GPU system will alias the memory as a raw format, allowing you to read and write to the pixels/blocks in their raw format. For sRGB textures, HTC sample texture provides an automatic conversion to linear when sampling. Oh yeah, to linear, right. When used as this, you will need to manually convert to/from sRGB/linear something like that. Okay, good. For block compressed textures, when used as HCC sample texture, the pixel will automatically be decoded from the compressed block. When used as this, you will be working on raw block data. This is useful when encoding block compressed textured data directly in shader code. And that's exactly what we'll be doing. So I'm glad we managed to combine that into a single sort of concept. It's just these are special texture formats which have a sort of raw counter or a raw component to them, basically. So maybe we can rename that to, rather than is sRGB, we could say has raw view. Oh, it has raw view. View's a bit of a weird word, but has raw format. And then we say raw format or format raw variant, something like that. It's probably better. And then we can also say C and GPU format raw variant. Very nice. Cool, so that's a much better name. Amazing. So let's go ahead and, what did I say? Raw has raw format. Yeah, let's do that. Has raw variant and is raw variant. Very nice. Cool, so there's that is sRGB. Let's go look around for that. GPU format is sRGB. Great, they're all used in here. GPU format has raw variant. And there's no other places in the code base that have done that. Then there's this other thing here, so let's see if that's used anywhere, just in Vulkan. There for now, so GPU format raw variant. Yep. Very nice. So that means then this would be initialized properly and we won't have to deal with this error anymore because it's happening because we're using unorm block compressed with the storage bits on. That is the reason why it's happening. Now I could do the better error codes, but I'll do that next time we encounter this problem. Sorry, better error reporting on this issue. Cool. So what another problem now is I don't think they're aligned properly. So we need to pick the biggest alignment. Right, I'm glad it's caught that. That's good. So when we do these two different storage views and all of this, it's just got to find. I'm putting it. Oh, yeah, good, right. So when we create our textures, now we've got this sort of like sample image, and then if it ends up being there's a separate raw variant, we create a new image with the new format and it's just a different alias. Yeah, it's just the same, sorry, it's an aliased piece of memory, but just a different image. And if not, we just reuse the sample one, like so. And the sample one starts off with a storage bit set, but if it has a raw variant, we remove it. Now, there's this memory requirements thing. So what we need to do is we need to say, okay, if for crying out loud. Right. So what we need to do is we need to pick the biggest alignment. You know what? We should probably use the storage one. That will always have the biggest alignment so far. So we don't have to do it twice. Although it is a bit hacky, you know, that could be hardware dependent for some reason. So I think we're better off saying if it has a raw variant. We'll do it again, but we'll max the results. So we'll be like raw, 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 and raw, but we'll combine the two now, right? So we'll say mem requirements. We'll take the size. The size will be the same. The alignment. And we'll say, okay, that's got to be the maximum. I think it's U64. Yeah, it's device size U64. So itself and then the raw version, we'll take the maximum alignment between those two. Then what we need to do is say for the memory type bits, we'll AND it with the raw memory type bits. So we'll only use the ones which overlap. It should be fine though. That should not change because they're both color formats. Yes, you won't have to do that. So the Vulkan spec states that if their color formats and have the same usage flags. Oh crap, usage flags. Oh, it might change. Yeah, let's do that just in case. All right. So let's run that again. Oh, we encountered the same problem. Oh, I'm using the sample image, not the storage image. All right, that'll work. So there's a new Vulkan error that we're going to tackle. Oh, for crying out loud, I didn't do it. Why didn't I solve it? Oh, the size needs to also be aligned as... Yeah, the size has to be aligned to a line. So I have to do the size as well. Okay, so no cutting corners there. Okay, so this new error here is to do with copy image. Copy image is not respecting the... What's going on here? The union of all source regions and all source destinations must not overlap in memory. Why do they overlap in memory? VBAA with the destination texture of doom doo doo doom. No wait, what's this saying? It's all on one line and it's so damn confusing. Are they the same textures? remind me how they overlap in memory? Right, handle image, this guy. Right. And then object 2 with the same handle. Okay. How did that happen? Did I change something with the... Let's git diff this thing. Texture copy somewhere. Oh, we had it. Oh. Yes, this is it. So we added these sort of block compressed things. Apparently added the line and maybe I changed some spacing. Yeah, I don't think we did anything crazy with this. Oh, let's read back. Let's get the music back. Yeah, we just added the source and the destination checks. There's no overwriting going on in here, it's just reading. So I guess the question is, are they the same? This is where we hop into debugger, I guess, and have a look. Okay. So let's print out the copy at the moment. So the copy is saying, so they're different destination and source IDs. And I'm gonna go on the box. Right, so open up these two things. I guess we'll go through all these. Right, let's get down to there. Oh, it says source. Ah, that is why. I put two sources into the back end. Whoopsie, I got too trigger happy on the find and replace. Alright. So I expect it to either, there we go, render in a very invalid way. So this is rendering as the block compressed format, but the texture layer we're writing in is not block compressed. That's running this every damn frame, isn't it? I forgot to undo that code. There's like an or one somewhere. Is there? So pass 0, look for that. Oh no, it's not running every frame. Why is it taking so long then? What's running? Been checking the profiler, what's that? "12 milliseconds, what's going on?" Oh. It's filling as invalid. Yeah, there must be one going on. It's uploading the, right, so... to do remove me, this is what I wanted to do. Right, that's why I was running so slow. Because I was doing this sort of like debug thing where I was hovering and running the... Anyway. Don't know why it's even slower now. Oh, I've got this debug code in here, I think. And I think it's running some like shader to do these debug lines and stuff. Sorry, to these debug. Let's disable those. Alright, I think so it's emitting per pixel into this draw thing maybe, or I don't even know, would that be? Oh, that'd be it. Render opaques, why are they so damn? Yeah, but yeah, these things are taking way too long. We must be doing something really dodgy with the texture sizes, or something like this. I think something is just painfully wrong. If we go to the visibility buffer AA, no, they're the right size. No, don't do this. Right, that got really choppy. We end up losing a bit of the, oh, okay. Yeah, something is really bad. We could try and turn off the block compression and see if that fixes it. That's in the settings now. So I got a settings file. Well, I haven't got a settings file. Right, let's change the encoder. Let's default it to off. Material compression off. And then rerun the code gen. Now let's run this and see if it's running dog slow. So we should see good texture now. That's actually running alright. So I don't know what it is with the block compression, but it seems to be messing up absolutely every shader. And I don't know why. Or I don't know, let's just could it be that we over allocated memory? Oh. That seems to be right. So if I turn on material compression now, and this turns on all that sort of block compression path. I didn't do the we did the code gen. Because currently I'm just using default values for the settings. That's causing shaders which don't even use this to be really slow. Oh, has it got overlap? No, it's not the overlap. Something really dodgy going on. Right, let's quickly look over the code to see what's up. So we've got this sort of like material compression. We just basically use block compressed, right? Okay. That's all we're doing. We can open up the texture viewer and see as well. Then in the GPU layer, we've got this. Nothing really changes in here. Oh, is it in blocks? I think it allocates in blocks. You know what it is? I know the exact bug. So I think the width. So I think one of the Vulkan APIs is taking in the number of blocks. I think. No, it can't be. But yeah, I think there's some overallocation going on basically of memory. And it's swapping the memory into RAM, CPU side, and causing us to have very slow GPU times because when it tries to access the GPU memory, it's not there. And then it gets the CPU to copy it to GPU VRAM. And it's causing it to be really slow. So we've overallocated memory, I think. And I don't have a way to view this in my game right now. So I'm pretty sure that's what's going on. So one way we can tell is we can just see basically if we go into Vulkan, there's this size thing here, right? It's looking all right. Now, what we can do is say don't know what happened to the music. So go, hey, if it's block compressed, just give me the number of bytes and I'll it's just a certain number of bytes. What I'm doing with the block dims is GPU format block dims resource texture format. Right, so if we'll assert. Make sure it's not block compressed, and if it's block compressed, then assert with this and tell me BC bytes equal this number. So that is memory requirements size. Right, let's see how crazy that is. Hey, Tapir, how's it going? Thank you for the raid, sir. Appreciate it. How you been? It's been a while. Welcome, raiders. Welcome stream. How's the stream? We're currently working on adding block compressed textures to the game. We've got these materials that we've made from our custom noise shader, which you can layer up noise and then color it in and generate some textures. Got normal maps as well. And yeah, we're trying to make these block compressed now. Well, all the color info and the metalness and roughness all block compressed. So we're just massaging the code a bit to get that going. So we've got ways to generate more shaders and more materials. And we'll be building a material editor in a bit as well. So any questions about the project, feel free to ask away. Come over, Stone. Exactly. Hey there very much. Yeah, exactly. Maybe I can get the sort of a yeah, nice hair from this. Pretty cool. Lots of potential. Currently it looks kind of like rocky hair. Like rocks, you know. Maybe there's ways to make it more wooden. Chaz helped me make a shader that reacts to sound. Interesting. So you're like taking the waveform and right. Nice. Yeah, I've heard things where basically, you know, and I understand it more than now I've looked into fractal Brownian motion, but I've heard it say that like that basically rendering and sound is kind of very similar because it's like a signal processing and stuff like that. And I don't know how far that goes though. It's just interesting. There's some overlap between rendering and audio. But I've never done audio, so I don't really understand the format. Alright, so how many bytes is this? See how so we're expecting 4K by 4K by 4 bytes per pixel. So that's 64 meg. Right, I think what we've got is 256 meg. So it's divided by 1024. Yeah, 256 meg. So what we got was 4 times the amount of memory. So there's something to do with block size. You know, it's using the block size rather than the pixel size. So there's something we've got to do, divide by block. So I guess the crate image info is in blocks. Let's have a look. Extent data elements. What does that mean? I think it's blocks. Yeah, I think we've got to divide by the number of blocks. It will work. So I think my suspicions are true. Then the reason why we're getting slow frame rate is because it's over allocating memory. We've got too much VRAM being used, so it's swapping out to disk. Like, it's swapping out to, sorry, CPU memory. And transferring VRAM out to CPU memory and being dog slow. So what we need to do is whenever we do this, it's in blocks. Hey, Swang Funk. Turned FFT, right, fixed Fourier transform, I can't pronounce this, Fourier transform, into a 1D texture. Nice. And sample that, cool. I've not actually played around with that stuff and fully understand it, but I get the basic idea. Yeah, with the way you, it's all of the inputs into cyan or something like that, and yeah, I've seen some videos, but I can't quite describe it. Oh yeah, I've seen people do FFT bloom with Fourier transform. They do that in Unreal Engine, isn't it? Where apply they apply like a bloom kernel of like a star or something like that, and they apply it across the whole image and get these sort of people. Oh, okay, they apply these sort of like bloom kernels of like that across the whole image, and somehow it repeats over the bright pixels. I have no idea how it works, but it's just magical maths. Apparently, though, it's more expensive than a standard bloom, so there is a big trade-off there. But yeah, pretty bananas. Yeah, say quite deep. Awesome. Oh, it goes quite deep, right? Uh, what up, Swang Funk? Just had your stream in the background as I was washing dishes. Oh yeah. That's what I do typically is I'll put on videos in the background when I do stuff. Good. You know, another one is working out. Put on a nice video. Yeah, family's good. My boy's now walking. He is now advanced to the next level. He's basically officially a toddler now. He walks and he throws tantrums when you say no. So he's developing into a fine toddler. But it's cool though because Now he's walking around. He's just interacting with his environment a lot more. And his current habit is like he likes playing with doors, so we're trying to stop him from not playing with doors and getting his fingers trapped in there. But we've been playing Astrobot's good fun, getting closer and closer to completing it. I sit him on my lap, and at the weekend we play a couple of levels. And I've nearly finished the game now. Like I've got all the bots from the main solar systems. I'm just in uh the extra solar system at the bottom, and I've got to try and do all the other post update bots and stuff. But yeah, it's great. Good game. Astrobot. It's like an old game, but made for modern hardware. It's just a good game. But yeah, family's very good, thank you. And it's summer now, so we're going outside more. We went for a good walk yesterday, went out, and my son got around to walk outside on ground, and he's enjoying it. Good times. An old Photoshop trick is to remove skin impurities, is to do Fourier that splits the image into three frequency bands where the middle one has impurities and you select and erase those parts there. Wow. I wish you could do that in Photoshop. Amazing. Obtain all skin structure. Cool. We said doors, right. Right. Yeah, I don't really know so much about sound and stuff, but yeah, fair enough. Okay. Right, so I think we need to put block dims in here, basically. Oh, this is going to mess with my texture viewer as well. Maybe. Well, no, because it samples it. Yeah, so GPU format, block dims, resource, texture, format. Right. Crap. Hang on a minute, I've got to do some I could return a vector 3. Block dims dot y and 1. Alright, jobs are good. Right, so we're going to take this code and find all the other places that Vulkan wants blocks. So it's here in texture copy. Think there. Copy dims. Then we need to go back. There's just so many places where it wants blocks. Well, there's only 4. But it's 4 too many. I think they must be the same block size as well. Yeah, they must be the same block size. Or will they? Ah, I've got to check this out. VK command copy image. What are you saying about blocks? Must be learned to multiple text or except for the edges of the image. If the format of the destination image has a different block extent than the source image, the offset and extent for each dimension sorry, for each of the regions specified is scaled according to the block extents of each format to match the size. I don't know how that makes any sense. Oh, it's saying if one is compressed and one is not compressed. Is that what it's saying? Because then it's saying if each of them are compressed, they must have the same textile extent. Yeah. We'll put that assertion in there. Right, that's good, that's good, that's good. So in GPU texture copy, then we can just say that destination equal source, and then say, oh wait a minute, I've got to do the all equal right here. We're saying that block dims mismatch. Can't be able to put more useful information in there. Right, so then in that case you get this one destination and you just need to check the source offset with block dims. Okay, so get rid of that second check. And jobs are good and right. So let's go back into this Vulkan code. And we need to find that sort of dims 3 again. Bring that in. And all we're looking for is the destination texture. Now, where are we getting that? Now, DST. And voila. Ah, that was... Right, so there's only a few more places to change over. So, where else we use an extent, a Vulkan extent, is an upload. I think that is going to be measured in blocks again. Go to buffer image copy. No, it's for BC. I'm not using ASTs because I don't think that's supported on PC. I think they're only supported on like Intel or something like that. I think there's one. I forget exactly what it was. Don't take that as the way it works. Let's see, quick. Yeah, they don't support ASTC, but they support BC. Yeah, they don't support any there. And then BC. Why doesn't he? Why are they like grayed out? I guess okay they'll grayed out because they completely don't support it. But yeah, they support BC on PC. Yeah, so again, this regions thing. What are we saying, right? The extent is that size in texels Does that mean the image copy? Don't do this. Is the image copy in texels as well? Must be multiple of texel block. Oh, so maybe they are talking about in texels. So maybe I don't have to change that one. For crying out loud. Extent. Right, must be multiple of the block extent height. Okay, I didn't realize there'd be a block extent depth. Has anyone ever done that? There's no 3D block compression, is there? Okay, good. Right, so I think then, when it comes to this, we just undo it. And the only thing that they needed it was the create texture, which was just bloody weird. And you know what, I might just make this a vector 3, even though they're never gonna have, well, yeah, someone might come out with a vector 3 one, and it just easier if we do it like that. Alright, I'll double check this thing again, but it seems to be working that way. Oh yeah, that was a study thing. Alright, GPU. So when we create the texture, we'll just keep it to 2D for the error codes, for the error checks. So now we do 3D. Alright, so 3D all the way. Yeah, let's do that for now, it's okay. Right, nearly that. NVIDIA had a VTC volume extension, which is S3TC BC block compressed, but oh right, extended 3D, no idea it was used nowadays. Interesting. Huh. That's cool. I've seen that actually in the code. I didn't realize that was what it was for. But that's good to know. Thank you so much. Yeah, I think I've seen it around in Vulkan. Maybe. I'll do it for now. How's it going, Cranston? How you doing, sir? There's just so many of these. Right. Oh yeah. Cool. Right. Oh crap. Hang on a minute. Oh yeah, and I've got these in the wrong kind of order now though. Let's just quickly move them around. Doesn't matter, but it's just keeping it consistent is all with what is the enum order in the header file. Right. So, the one thing I want to double check was the create image. So I'm confusing. So it was, the bug was having is creating it 4 times larger, or 16 times larger, I think maybe. So I think that's because extent, number of data elements. That's readable. We're kind of looking for like blocks, basically. Right, so they've got this thing where it's like texel block. Block texel view compatible. So I alias the memory. So I kind of go around this in a way. I don't know if it's going to work. Yeah, maybe I should have a way to turn it off when I don't alias the memory. I create 2 different Vulkan images with the same memory address. Type of texel blocks. Okay, alright, let's go. Let's see how that works. Oh, we deleted the code which removed. Hang on a minute. Right, offset.xy. Yeah, so I've removed the code which got the size of the memory that is allocated. Okay, seems like it's, oh no, it's not. Oh, so hopefully it's running fast now. Okay, this is interesting. What do we got? Ooh. So it's saying that when we copy the memory to so I guess we're copying the the material. The source offset plus extent exceeds the source resource width of 32. So that is a multiplier of 4 off, right? Which means it's got to be using the block size instead of pixel size. Everything's so damn confusing. Just measured in blocks. So we are going to have to do that thing. But we read it, and it said vk copy, sorry, command copy image. We read that it said yes, it said texel, and that's what got me confused. It said texel. So what it means by texel then is the block. Because I went into here and I saw the word texel. So what they mean by texels here is actually a block. Alright. So yeah, I need to go back into the Vulkan code and be like, okay, image copy, and then that means the other ones is going to need it as well. So, right, divide. Okay, so we'll do that again, but for the upload is probably going to work the same. We divide by the number of blocks. We've already ensured in the layer above that there are multiplier exactly they're an exact multiple of the size of a block. Right, thinking about it, this will need to be resource. Source texture, destination texture. Right, I think that's it then. We keep going around. Right, that's it. So we run that. So we should be seeing some really painfully initialized data of the albedo and emissive. It's completely wrong, right? So it's in block artifacts, right, as you would expect, because we're encoding the pixel data of, we're encoding standard pixel data for an uncompressed format into these pixels, something like that. Right, and now the frame is actually running as we expect it to run. Before it was running very, very slow. It was running like at 30 ms, because what it was doing is it was swapping the memory out from VRAM to CPU, because we over allocated too much memory, basically. That was what was going on. So if we take a look at the block compressed size, this would be an interesting one. We did this a second ago, so let me just sort of undo all these changes because I deleted the lines. Here we go, these lines. So 2118. Now we get to see how much the block compressed is, how much it's helping us. I think this will be for albedo. How can we tell? Yeah, the first one that gets called is for albedo. So we'll get the size here. It's now this number. So the number, okay. So we take the, yeah, I wonder if we should divide and keep it in pixels, or have, yeah, I think we'll have pixels. Vulkan likes to do it in blocks though. I think pixels is useful. But yeah, okay. So if we take a look at that number, it's divided by 1024 and 1024. Right, so it's 12 megabytes. So this for 4K, like 4K squared, so 4096 squared with RGB, right? RGB UNORM. So this is BC1. So it's 12 megabytes in VRAM. And then that will be, so for a 4000 square texture, right, with 1 byte per pixel is 16 megabytes. But if 4 bytes per pixel is 64 megabytes. So we're saving, you know, so what am I doing? It's divide by 1024 and then divide by 1024. And then, which way around do you do it? Wait, so it's 12 and 16, isn't it? So it's, yeah, I think it'd be 12 over 12. Yeah, so it's about 5 times more memory to have it in RAW in an uncompressed format, basically. So that's the sort of savings we're looking at for a 4K texture. So that's a lot less pollution in the caches of the GPU, and that should hopefully help with speed when it comes to sampling and stuff like that. And obviously just use less VRAM and we can use the VRAM for other things. But it comes at the cost of quality because it is a lossless compression. Okay, so we're at the stage now where we can at least run the game, but we're populating it with invalid texture data. Oh, wait a minute, I did just say we can at least run the game and then it crashed, but it's because we had that code in there. So we're just viewing it with, we've got this sort of invalid texture data. So now what we have to do to get these super lovely textures back is we have to take our we have to do the block compression ourselves. So we're going to do it in GPU memory because I don't want to put it to disk and then run it through a third-party program. I want to just do it directly on the GPU because the data is on there. We generate the materials on GPU. So let's just port this code here, which is open source from, believe it or not, from the Xbox team at Microsoft somehow. And it will compress BC1, 3, 4, and 5. And it's all in a single header, so we'll port it over to the custom compiler that we have. It's not so bad, it's about 600 lines. And we should hopefully be able to get this working next stream. So that's what we're doing in the next stream, which will be on Tuesday, about 3 hours ago, but on Tuesday. And Thursday, I think we'll, yeah, I'm sure we'll be doing Thursday. Something to do with the material builder, because we'll have everything kind of ready to start working on the material building system. And sort out the code for that. Alright, so in the meantime, guys, there's a Discord channel. Thank you for everyone who's supporting the channel. Appreciate you guys. There is access to the source code if you support the channel via Ko-Fi or Twitch. There's more information about that on the Discord itself. In the meantime, have a good start to your week, start to your work week, guys. Have a good Monday. Raid Abner. Not seen Abner stream for a good while. Right. Cool. Have a good one, guys. I'll see you all in a future one. Catch you later.